Alright guys, this video is going to go through the diode lab. We're going to start off taking some voltage and current readings across a resistor, and then we're going to put a diode into the circuit and see how things react. Remember that a diode in reverse bias is going to block current. In forward bias, it will allow current to flow, but only after a certain voltage is impressed across the diode. If it's a silicon diode, then you need a minimum of 0.7 volts in order for the diode to start to conduct. With this lab, the main characteristics of the diode are going to be looked at, meaning that we're going to look at the characteristic curve. We're going to look to see that it requires a certain amount of voltage, 0.7 volts, and then after that 0.7 volts, it will start to conduct. The main things that we need for this lab would be our Festo electronics trainers. You're going to need the benchtop digital multimeter, and you're also going to need a handheld fluke multimeter. From your parts, you're going to need the 1N4007 diode, and then we're going to use a 100 ohm resistor. Okay. On this page, you can see the simple setup here. We've got the 0 to 25 volts DC. We've got the current going through the ammeter. Okay, we're going to be on the 2 amp jack. And you can see that it's DC voltage and DC current. Across the resistor, the 100 ohm resistor, we're going to have a voltage meter, so that'll be where the fluke is. And we're just going to take our current and voltage readings on the 100 ohm resistor. Okay, looking at this diagram here, you can see that we've got from the positive here, we're going to go into our ammeter. So our ammeter is going to be in series with the load here. You can see there's a jumper here. And on these trainer systems, there are jumpers between all 4 of these terminals here. So the circuit is essentially this: from the positive through the ammeter, through the resistor, and back to the negative. Nice, simple circuit. Across the load, we're going to take in parallel a voltage reading, and you can see that there's a jumper here, so we can drop in the terminals for the voltmeter across here, and we'll be able to measure the current and the voltage as we increase our source voltage. Alright guys, so let me show you one setup that you could do, because we have our choice of using the fluke meter or the digital multimeter. So right now what I've got is I've got the DC source. The DC source is going through my meter here. I'm on the 10 amp connection, and then we're going from the common over to the resistor, and then from the resistor back to the source. So at the moment I have my fluke meter as my ammeter, and I've got my digital multimeter as my voltmeter. You can see that these 2 connections in parallel with the resistor are going over to this meter, and you can see that I have 1 volt here, and I've got 1 volt on my power supply. So setting it up like this, using the fluke as the ammeter and the digital multimeter as my voltmeter, we can see that the voltage will mirror very close to whatever the power supply is. So right now the voltage here is 2 volts. I've got 2 volts on the power supply, and I've got 0.02 amps, which works. Okay. The only problem with this is that when you set up this lab, oftentimes if you guys change the setting on the meter, then you'll end up blowing the fuse inside this meter. This fuse is quite expensive, so we're going to switch it up. And we're going to use the digital multimeter as the ammeter, and we're going to use the fluke as the voltmeter. Now we can see here, let's just keep going up in voltage here, because this is a cool phenomenon. You got 3 volts here, and we have 3 volts. Now on this trainer here, I can move it up a touch, and the voltage doesn't change. You can see that the voltage slowly increases on the voltmeter here. Okay, but we're still mirroring quite well. 3 volts here, 3 volts on the power supply, and 0.03 amps. Excellent. Okay, I'm going to switch it up, and I'm going to use the digital multimeter as the ammeter, and then I'm going to use the fluke as the voltmeter, and we'll see what happens to the circuit. Okay, so this is how the lab has actually asked us to set it up. We have our fluke multimeter. We've changed this to now DC voltage, and we've changed our terminals here to the common and the voltage terminal, and we're looking at in parallel with the resistor, so we should be able to see the voltage there. The current from the source is now going through the digital multimeter. So we're going through the 2 amp connections here. So we're going through, let me just drop her down here. There we go. So we're going through the 2 amp connections, and I have my positive here, and then I have my negative going over to the top of the resistor, and then to complete the circuit we've got a jumper here going back to the source. The source that we're using is the DC output. Okay, so and again, in order to change that DC output, then we have to click on this button, and then we can increase the voltage. So I'm going to increase this voltage up to 1 volt here. Okay, and you can see now a little bit of disconnect. I have 1 volt on the Festo unit, so you would think that I would have 1 volt out here, but I don't. The problem is that this meter itself has an internal resistance. So you can see that the voltage here that we're seeing and the current is matching, right? So I have 4.9 milliamps, but this voltage here on my power supply is not being mirrored here anymore. So you would think it'd be the exact same as the previous setup, but by changing meters, I now have a meter that has an internal resistance. So what we're going to do for this lab now, we'll keep it set up like this because it's easier for me to switch out this fuse on this unit rather than the fuse on the Fluke. But we're going to now use this voltage as our reference because as I increase this voltage and get up to, let's see, 1 volt here, right? Then on the Festo unit, it's reading 1.1 volt. So again, from the source, there's a small voltage drop across these terminals, and that voltage drop is reducing that 1.1 volts down to the 1 volt out in the field. So it's cool. You can see that different meters will affect your circuit depending on their internal resistance. So, all right, guys. So this next part is going to be just basically looking at Ohm's Law. So what I want you to do on the meter is I want you to put it onto manual, right? So keep it onto manual here, and again over here we're going to have this on manual as well. And obviously for this first part, if we have 0 volts, then we're going to have 0 current, right? If we bring this voltage down to nothing, no pressure, gives us no current flow. Okay. The next one it says is it's going to increase the voltage to 0.5 volt. So again, we're going to use this as our reference for our voltage because this is right across the resistor, and we're going to increase the voltage here to 0.5 volt. Beautiful. Okay, so we have 0.5 volt now. We've got 100 ohms, and so we should see 5 milliamps of current that's flowing in the circuit now. Excellent. Okay, you can see there that I've got 5 milliamps of current that's flowing with that 100 ohm resistance and that 0.5 volts that's been applied. Okay, next one, we're going to just go up. Looks like we're going up by 0.5 volt for each of the increments, right? So if we increase this voltage up to 1 volt, there we go, just slowly adjusting until we get to 1 volt applied there. So we've got 1 volt and we've got 100 ohms of resistance, and so that value there should be 10 milliamps. Yes, we got 10 milliamps flowing in that circuit. Okay, if we keep going here, then you can see that for each of our 0.5 volt increase, we're going to have 5 milliamps increase there based off of Ohm's Law. So 1.5 volts is going to give us 15 milliamps, 2 volts is going to give us 20 milliamps, and so on, all the way up to 5 volts. So our last voltage here is 5 volts, and you can see here with Ohm's Law, 5 volts at 100 ohms is going to give us 0.05 amps, and if we move that decimal place over 1, 2, 3 decimal places, it would be the same as giving us 50 milliamps. Okay, so let's do that. We've got 1 volt. Let's crank this up to 1.5 volts, and we'll see the current value as we go up by each 0.5 volt. Okay, so there's 1.5 volts, and we should see 15 milliamps. Okay, let's go back again. Let's go up to 2 volts. Okay, 2 volts should give us 20 milliamps. There we go, 20 milliamps. Okay, if I increase the voltage again up to 2.5 volts, then we should see 25. Excellent. Okay, now I'm going to increase it up to 3 volts so I don't make you dizzy with the camera here. So we got 30 milliamps. Then this is 3.5 volts at 35 milliamps. And we just have this linear increase in current. 4 volts giving us 40 milliamps. 4.5 volts giving us 45 milliamps. And then finally our 5 volts giving us 50 milliamps of current. Okay, the next thing we're asked for is to graph out those values. So with every half volt increase, we're just finding that we were increasing the current flow by 5 milliamps. So you can see here they have that nice linear relationship between the voltage that's applied in the circuit and the current that actually flows in the circuit. All right, next thing we're going to do is we're going to throw in the diode now. So we've seen that increase in current flow with the increase in voltage across the resistor, but now we're going to throw in the 1N4007 diode, and we'll see how that affects our current flow in the circuit. You can see that based on that diagram, we've got the source from the positive going through the ammeter, then through the resistor, 100 ohm resistor, and then in series with the resistor we have the diode, and in parallel with that diode we're going to have the voltmeter. So the voltmeter is going to be measuring the voltage across the diode, and the ammeter will be measuring our total current flow in the circuit. Okay, so before we start and put this diode into the circuit, let's test the diode out. So the first thing we're going to do, if we're using the fluke, we're going to move the setting over to here, so continuity and the diode setting. In order for this to come in, for this diode setting, we have to hit the shift button, and then it moves us over to the diode setting. Okay, we know that we need to put the positive to the anode, and we need to put the negative to the cathode in order for this guy to conduct. Okay, so you can see a positive to the anode, negative to the cathode, and you can see that we have 0.6 volts being impressed across that diode. Remember that the 0.7 volts only comes in when it has the max current flowing through that diode. So we can see here that it's forward biased and it is conducting. Let's take out these leads and let's put it in reverse bias. In reverse bias with the negative to the anode and the positive to the cathode, then it should give us an open circuit. Excellent, so this diode's good. Let me show you how to use the other multimeter, and we'll test out the diode as well. Okay, using this meter, if you want to do the diode test, then we've got to get into this setting right here. So again, we'll hit shift and the diode, and that will bring us into the diode setting. Here we're on again we're on the common and we're on the voltage terminals for our leads. This is my negative, so I'm going to put my negative to the cathode, and I'm going to put my positive to the anode, and at that point I have forward biased the diode, and I should see that same 0.6 volts that's dropped across it. Again, in the textbook it says 0.7, but again the 0.7 will come in when it's actually conducting the max current. Excellent. If we now take those two leads and then reverse bias the diode, so we'll take the negative out here, we'll put it to the cathode, and we'll put the negative to the anode, the positive to the cathode now, so now we're reverse biased, and at that point we should see that it's an open line. Excellent, so we've used the 2 meters now, and we can see that that diode is good. Now let's put it into the circuit with the resistor. Okay, so let's set this up. We've got the voltmeter again on DC volts, and just be careful that you don't short out any of the components. Sometimes what you guys will do is you'll take the resistor and you'll put it across here, and you can see that you'll short out that component. So I'm going to put the resistor in first, and then I'm going to put in the diode, and based on this diagram here we can see that the diode is forward biased. We have the positive to the anode, and we have the negative to the cathode. Again, on our diode it shows us the exact same symbol there, so we're just going to place it in. Again, we're making sure that we're not shorting it out with any of the jumpers there, we'll drop that in so it's forward biased. And then our DC voltmeter is just going to look at the voltage right across these two terminals. Okay, so you can see here my results before we start this. Remember that the diode has to have 0.7 volts across it before it actually starts to conduct. So you can see that all the way up to where I have it started there at 600 millivolts, right? That's 0.6 volts. There's really no current flowing. I've got the microamp meter there, 0.13, 0.26, 0.79, 8.6 microamps, 28.6 microamps, 112 microamps, 391 microamps. All those guys are basically no current flowing whatsoever. Then we'll find that as soon as we get close to 0.7 volts, right, so at 0.6 volts, all of a sudden the current is going to start to skyrocket from microamps all the way up to milliamps. So then I had 1.27 milliamps, and then as my voltage increased, the diode was conducting more, and I got 3.88 milliamps, 12 milliamps, 37, and then all the way up to 127 milliamps at 0.8 volts. Okay, so let's take a look. At this point, we'll start off with no voltage whatsoever. And obviously with no voltage, we get no current, right? Okay, let's go up to 50 millivolts. Easy now. Okay, 50 millivolts, I'm getting nothing, right? You can see that I'm on microamps. It's essential at this point for you guys to be in automatic. So we'll flip over into the milliamp once we adjust the voltage higher. So make sure you're in auto, and let's just slowly increase. This is 50 millivolts. Let's go up to 100 millivolts, nothing flowing. And then we're going to go up to 150. So there's 150, nothing flowing still. Okay, let's go up to 200, still nothing. 250. It looks like there's current flowing, but that's 0.25 microamps, so it's nothing. Let's go up to 300 next. So there's 300, still getting microamps of current. Here's 400. The current looks like it's increasing, but again, we're in microamps. You can see this value right here, right? So at 400 millivolts or 0.4 volts, we're getting nothing. We need 0.6 or 0.7 for this guy to start to conduct. Here is 450, still in microamps. Here is 500. Okay, we're still in microamps, and right now we're at 500 millivolts. Okay, we're going to go up to 550. Taking a little bit more time to go up now. Okay, 550, and we're still in microamps. Now watch what happens when I go from 550 to 600. Okay, so it's 560, and as soon as I went to 570, then all of a sudden that current increased. Let me go back down to 550. Okay, you can see that it just stopped conducting, and I'm going to go slowly increase. Okay, so that's 560. At 570, then all of a sudden it started to conduct. So now we've got 2.75 milliamps, and that's at, let's see, at 600. Let me go back down. At 600, I'm getting 1.32. And then you can see that as the voltage starts to increase, because the diode is now conducting, then we're going to get more current flow. So there's 650. At 650, I'm getting 3.98. At 700, watch this. So you can see here, here's 650. Let me go back down. Okay, at 650, the value comes in, but then if I keep increasing the voltage, then it says open line. So at that point, I'm going to move over to just voltage, and I can increase this to 700 millivolts or 0.7 volts. And at that point, before I was getting 12 milliamps, and right now I'm getting 13.7. Okay, so we're actually getting the current to flow once the diode has conducted. Okay, once I go up to 0.75, then I'm getting 38 milliamps. And then as soon as I go up to 800, then the current starts rocking. I got 0.77, 0.78, 0.79, and this is 0.8 volts or 800 millivolts. At that point, I've got 123 milliamps, and previously I got 127 milliamps. So the main thing to see here is just that it needs a minimum of 0.6 volts in order for it to conduct. Once it conducts, then all of a sudden you can see that exponential increase in current flow once the diode has reached its threshold voltage. Okay, when we graph this guy out, we can see that characteristic exponential increase in current. We had nothing, and then around 600 I started to get some milliamp of current. Then all of a sudden around 0.7 volts it started to conduct, and then you can see that exponential increase in current. Okay, so last part we need to do here, guys, is we're going to flip the polarity of the power supply. Okay, at that point the diode is going to be reverse biased. If it's reverse biased, if you look at the cut sheet for this 1N4007, it can deal with 1,000 volts peak in the reverse direction. So we can increase this. What are we going to increase it to? 16 volts? No, sorry, that was reading number 16. We're going to increase it to 25 volts across that diode. Well, in the reverse bias, meaning that we're going to have positive here and negative here, this diode will be able to block up to 750 to 1,000 volts. So there's no way that it's going to conduct. We'll see no current whatsoever on the ammeter all the way up to 25 volts, but we will see that the source voltage is going to be mirrored across the diode. Okay, so what I'm going to do is I'm going to change the polarity here. So by doing this, I'm going to now reverse bias that diode. I'll turn this bad boy on. So if you're changing anything out, then just turn off the power supply and then turn it back on. Okay, and then we're supposed to go from 1 volt, 2 volt, look like we're going in 1 volt increments up to 10, and then we're going to start to rock and roll. So we're going to increase this guy, and we can see that, here, let's go off of this guy. So this is 1 volt right there, okay, and we can see that the voltage, so now we've got a negative there across the voltmeter because we are reverse biased, so we're getting the negative on our meter now. And let's go up to 2 volts now. So this part of the lab we should be able to rock through. There's 2 volts, okay? 2 volts on the power supply and 2 volts dropped across the diode. Okay, let's go up to 3. Now again, based on that cut sheet, we can go up to 1,000 volts and we're still going to see that voltage across the diode, which is amazing. So 3 volts on the power supply, 3 volts across the diode. Okay, let's just keep rocking and rolling. Here's 4 volts, 5 volts, so the diode is mirroring our source voltage. 6 volts, 7 volts, okay, just to make sure you believe me, 7 volts on the supply, 7 volts on our diode here. You can see by the negative that we're still reverse biased. 8 volts, 9 volts, 10. Okay, next one we're going to go to is 12.5. Okay, so there's 12.5 on the source and 12.5 on the diode. Okay, then we're going to go to 15. You can see how this is going. Everything's the same. 15 on the supply, 15 on the diode, 17.5. There we go, 17.5 on the diode. Okay, we're going up to 20 volts now. And we got 20 volts across the diode, 22.5. There we go, still mirroring that image. And then finally, 25 volts. There we go, so 25 volts on the source and 25 volts on our diode. Okay, now I haven't shown you the ammeter, but this is 25 volts, and you can see that there's absolutely no current. We got 2.47 microamps of current. Okay, I can drop the voltage down. Right, there's 20 volts. We still have no current whatsoever. This supply voltage goes up to a maximum of 25 volts. So at 25 volts, we're seeing the same voltage impressed across the diode, but we're seeing absolutely no current whatsoever. The diode is not conducting in reverse bias. Okay, so this graph right here is almost comical. The reverse bias here, you can see that even at 25 volts, we're getting virtually no current flowing whatsoever in that circuit. All right, guys, so just for a synopsis here, in the forward voltage, we saw that around 0.7 volts at the knee voltage there, we started the diode actually conducting, and then we went exponential in our current flow. In the opposite direction, when we took that diode and we put it in reverse bias, well, we never reached this reverse breakdown voltage. This reverse breakdown voltage for this diode is around 750 volts. So at 25 volts, we're nowhere near. Okay, so forward bias with the positive to the anode, negative to the cathode, we have to increase the voltage to 0.7 volts. Then we saw that exponential increase in current. And in the reverse bias, it essentially blocks the current. All right, guys, thanks very much for your patience.